Okay, so let's continue with the lecture on the logic graph and stick diagram and so on. Okay, so we'll continue with this, the OAI 2-1 logic graph. So OAI here means the OR and is a OR and 2-1 gate, and the circuit schematic is given here. Okay, so 2-1 refers to the 2 there and a 1 there. Okay, so it's a OR and invert gate. Okay, OR and invert, or the invert there. Okay, so OR and invert, so you can see is A plus B. So it's actually C A plus B invert. So A plus B, we have the parallel in the NMOS configuration, and we have the series in the PMOS configuration, and then C dot A plus B, so the C is in series with A parallel B for the NMOS, and for the PMOS, the C is in parallel with AB in series. Okay, so on the right side here we have the we have the logic graph. Okay, so how do we make the logic graph? We start with the VDD on the right side, we have the ground on the lower side, and then the X here is your output. Okay, so your main gate output X. Okay, so X is actually there, and then you also have in the middle of the graph you will have nodes I and nodes J. Okay, so node I corresponds to the node in the NMOS configuration, and then you have the J in the PMOS, the node J in the PMOS configuration. Okay, so how do you obtain the graph is basically each line here corresponds to a transistor. Okay, so for example, let's look at transistor A. Okay, transistor NMOS A. So A is connected by the node I and ground. So you can see here that A here is actually connected from I to ground, and then we have B is connected from ground to I. So basically you have something like this, A and then B from ground to I, and then from I to X you have the C. Okay, the C edge on the graph. Okay, so as for the PMOS, is the same story, the same thing. So let's look at the A. So A is from VDD to J. So A is from VDD to J, and you can see there's a cross between the PMOS. Okay, and here is your NMOS. Okay, so so we have a cross there. So A from VD to J, and then J to X is a B. So J to X is a B, and then we have from X to VDD is a C. Okay, so you obtain this graph, and from this graph you want to actually the purpose of the graph is to find the optimum. So the purpose to find optimum input sequence. Okay, input sequence for layout design. Okay, so the purpose we do this graph is to find the optimum input sequence. So the sequence can be ABC, ACB. You know, we have 3 inputs. So what is the optimum sequence? And from that we have to use the so-called Euler path. We need to find the Euler path. Okay, so basically when we talk about the sequence, to do the physical layout, we can have many different sequences. So we can make a layout where you have ACB, ABC, and so on. So if you're not familiar with stick diagram, so basically what happened here is we have this is your polysilicon gate. Okay, so your transistor here is out here is your PMOS, and down here is your NMOS. Okay, and then here is your so for PMOS you have a P plus, your P plus diffusion, and here is your N plus. So the green side there is actually your N plus diffusion. Okay, so your transistor, for example, here is your gate of A, and here you have the source and the drain. Okay, so here is connected to VDD, so A is actually your source and your drain there. Okay, so you can see that your A transistor, okay, so your A transistor is connected, the source of the A transistor is connected to VDD, and the drain of the A transistor is actually connected to the possibly the source or the drain of transistor B. So you can see here, so actually A is connected to VDD and B. Okay, and B is connected to A and X. Okay, so you can see from here, B is connected to A and X. Okay, and you can see X here is also connected to X here is also connected to C of the NMOS. Okay, and the C of the PMOS. So X connected to the BC of PMOS and C of the NMOS. So you can see here that X is actually connected to here is actually B/C. Okay, PMOS. Okay, so we have a shared diffusion. So here you can say it's a shared diffusion, BC. So and X is also connected to here, okay, which is the drain of C NMOS. Okay, so if you make the connection correctly, so for example, the A of the NMOS, okay, so here is the A of the NMOS is connected to ground and X and so on. So so the first step is to make the polysilicon gates, and then to draw your diffusion, and then here are your metals. Okay, the blue part here, metals. You have your VDD, you have your ground. So the way to make the layout, you can have many different configurations of the layout. Okay, for example, if you do ACB, something like this, and if you do ABC, you're going to get something called the uninterrupted diffusion strip. And for ACB, you actually have the interrupted. Okay, so let's have a look quickly what it means by interrupted and uninterrupted. Let's remove all this. It's a bit messy. Okay, so so we see here there's an uninterrupted diffusion strip, the N plus, and here we have the interrupted. So you can see there's an interrupted. Why is it interrupted? It's because let's have a look at the C and B transistor for the NMOS. Okay, so the C and B for the NMOS is given here. The C and B for the NMOS, and the B is connected to ground and C. Okay, so B is connected to ground and C, and then C is connected to X and B. Okay, so in fact B and C we can share the diffusion, but in this case we cannot share because we have an interrupted diffusion strip, because it doesn't conform to the Euler path. Later on we'll see what the Euler path is, but let's have a look here. So for transistor B, is connected to ground, and is also connected to here, right? So it's connected to B is connected to ground, and is connected to A and C. Okay, so we can see here B is connected to ground and is also connected to A and C. At the same time, C is connected to X and to A and B. Okay, so C is connected to X, which is here. Okay, and then it's also connected to A and B. Okay, so A and B here. Okay, so here is A, C, B. Okay, so here is AC connected to the B. Okay, so so we could not connect the X directly to the ACB. Okay, so we have the interrupted diffusion strip there. Okay, so so basically you can say we can have multiple different kind of sequence of input, and each will give different kind of layout, and which layout is better, it must conform to the Euler path. Okay. An uninterrupted diffusion stream is possible only if there exists a Euler path in the logic graph. So what is the Euler path? A path through all nodes in the graph such that each edge is visited once and only once. Okay, so let's have a look at this example here. So so remember each line there is a transistor. So if you do the ABC ordering, so we go A, B, and C. Okay, this is for the PMOS. Okay, and for the NMOS, it must conform to the same one. Okay, so for a single polystrip for every input signal, the Euler path in the PUN, PDN must be consistent or the same. Okay, so means that for the NMOS, we also need to have the same ABC ordering. So here, can we get the ABC ordering for the NMOS? So we can. So we see here we say A, B, and C. Okay, and we actually travel through every node in the graph once and only once. Okay, so so A, B, C. Okay, A, B, C. Each edge is visited once. Okay, not node. So each edge is visited once. So you say A is visited already, so cannot visit anymore. Now B is visited. Okay, done, and then C is visited. So we managed to visit every node once. And the ordering is the same for the PMOS as well, where we can also visit one time. Okay, so A once, done, B done, C done. So we are visiting each edge one and only one, and we have the same ordering for the NMOS and the PMOS. So that is called a consistent Euler path. So then our layout is going to be ABC, something like this. Okay, and then you have the diffusion strip, you can have the metal connection and so on. Okay, so this is for the ON invert 2-2. Okay, so ON invert 2-2. Can we find the consistent Euler path here? So let's see. So ABDC. So for example here, consistent Euler path can be A. Okay, so A visited already, not allowed to visit anymore. And then B. Okay, and then C, and then D. Okay, so AB. So let's see ABDC. So let's look at, let's use the same example. There are many. There can be more than one Euler path. But in this case, let's try ABDC. Okay, let's try AB. Okay, let's try ABDC. So ABDC. Okay, and can we get the same for the PMOS? So ABDC. Okay. Remember, you need to draw first your graph. So your X output on the left and at the top, and then you have your ground in VDD bottom on the right, and then you also have your internal nodes. Okay, your internal nodes there. Between C and D, let's call this I, J, and K. So between A and B, you have the I. So this is your I node. This is your J node, and here is your K node between DAB for the NMOS. Okay, so you draw your logic graph, and then you check if there is a consistent Euler path or not. So for example, ABDC, ABCD can also be a consistent Euler path. Let's have a look for ABCD. So that. So ABCD is good for the NMOS. ABCD okay, so ABCD might not be good for the PMOS. So let's see, ACDB. Okay, ACDB works. Okay, so if you go like this, ACDB. Okay, and then we can also go ACDB. Okay, so ACDB is another Euler path. So you can have more than one Euler path, and the Euler path will guarantee us the optimum layout. Okay, so let's have a look example here. So if you do ABDC, then we don't need to split our diffusion region. Okay, so so okay, so ABDC, so we can see here, you can just make your poly. So if you want to draw, so let's try and draw this a little bit. So if you need to draw for yourself, ABDC, let's do something like this. Let's do through here. Okay, so if you have to draw, so it's ABDC. So we have the diffusion. Let's put the diffusion like this. Okay, okay, and then we can see that the A, okay, so here is the A transistor is connected to VDD, and this is I, J, and K. A is connected to VDD and also B. Okay, so so here is your metal, VDD, and then here is your ground. Okay, so one side of A is connected to VDD, and let's connect this one to this one, so metal there. Okay, so A is connected to VDD, and then A is connected to B. It's automatic connection, so we have a shared diffusion here between A and B, and then B is also connected to X and D. Okay, so X and D, so B, D, and X is connected together, so we can go like this. We can say something like this, and this is your X. Okay, so now X is connected to also your B and D, and then your D is connected to C and X. So D is connected to C, which is there, and then is connected to X. Okay, so that's done. C is also connected to VDD, so you need to have another one there. Okay, so C is connected to VDD and also connected to D, and then D is connected to C and also to X. So done with the PMOS, and for the NMOS, you have the AB connected to ground. So AB connected to ground, we can do a shared diffusion there. Okay, so AB both connected to ground, and then you have C, D, AB all connected with K, but the C and D is connected to X. So C and D is connected to X, you can do like this. Okay, so CD shared diffusion connected to X, and then you will have finally sorry. So CD is connected to X like this. Okay, so CD is connected to X. The other part of the C is connected to everything. Okay, so here is going to be something like this. Okay, so here you have to jump metal. Okay, so that we don't short it. Okay, something like this. Okay, so now we can see that one part of A is connected to BD and also connected to one part of the C. Okay, so this is the so-called stick diagram, and you need to know how to derive the stick diagram from a given Boolean equation. Okay, so given a Boolean equation, you need to first derive the transistor level schematic. From the schematic, you need to, okay, so it's step 1, step 2, step 3 is the graph, step 3 is the graph, step 4 the Euler path, and then step 5 is your stick diagram. So 5 steps altogether from a Boolean equation to the stick diagram. Okay, so one thing to note here is that some functions have no consistent Euler path. Okay, so if there's no Euler path, then you will need to split. Okay, split your diffusion. Okay, split diffusion if no consistent Euler path. Okay, later on we can see more example of that later on. Okay, so that's it for this video on the stick diagram.